In this video we're going to learn about atomic arrangement. Let's put this in context with our earlier studies. What we just learned in the previous learning module was that the electrons around the atoms, or around the nuclei in atoms, have a certain structure. This structure determines the type of bonds that form between atoms. And we talked about different kinds of bonding. The results of those different kinds of bondings results in an atomic arrangement. And that is the subject of our study in this learning module. Atomic order can be classified according to the extent of order or regularity. For instance, in a gas, there is no order of any kind. The positioning of the atoms is completely random in a monatomic gas. In a liquid, neighboring atoms may show some regularity in their positions relative to each other. However, as we move a few distances in terms of the distance between atoms away, we find that the probability of finding an atom in a certain place is completely random. In a crystal, we have long-range order. The atoms are stacked in a particular regular sequence. The different types of order are shown in this, or are illustrated in this diagram. In category A, we have the monatomic gases, which have no order. Category B, we have materials with short-range order. These materials are called amorphous materials, and they include materials such as glass and plastics. Liquids also have short-range order. In category D, crystalline materials may be classified into two subtypes. Single crystals. In a single crystalline material, the stacking of the atoms is perfectly regular, or I don't want to say perfectly, that would only be true in a perfect crystal, but the atoms are stacked in a regular order throughout the whole volume of the solid. That's a single crystal. More common is a polycrystalline material. Polycrystalline materials are composed of smaller crystals that are bound to each other. When most people think of crystals, they would be thinking of something like this. This is a crystal of amethyst, and we can understand how early humans, coming upon something so regular and beautifully faceted in nature, would consider these things special and magical. However, not all crystals look like that. Let's consider a humble piece of steel. If we were to polish a cut section of the steel and look at it under an optical microscope, we would see that it is made of tiny grains. Each of those grains is a crystal. What do we mean by a crystal? When we go to the grocery stores, we find that a method to pack oranges in the most efficient possible way is often used. We can see the oranges form a regular repeating pattern. If we put crosses on the center of each of those oranges, we see that we find a regular pattern. For instance, all of these are aligned in a straight line, etc. We could find many examples of symmetry in this arrangement. This is the great analogy for how atoms stack in a material. However, there are many different ways in which atoms can be regularly stacked to form a crystal. And we, as material scientists, we have to find ways to describe the different types of crystalline structure. Let us first start with a lattice. A lattice is a theoretical construct from mathematics. It is an infinite three-dimensional set of points such that each point has identical surroundings. Or in other words, the points in the lattice repeat in space in a periodical manner. Let's have a look at our oranges. You see that the crosses I have placed upon the centers of each orange form part of a lattice. It would only be a lattice if we looked at an infinite plane of oranges. But we can imagine that these blue crosses form part of a lattice. We can see that if we go in one particular direction, let's say directly towards the right, we can see how the lattice points repeat in a regular manner. Of course, the oranges are not all uniform, and so there is some variation in the stacked oranges. But if this were an element and the oranges were atoms, then all the atoms would be identical, and there should be no reason why the distances between the lattice points should vary. Unless there were defects, of course, which do occur. So we can see that if we got rid of the oranges and just had these lattice points, that would give us a mathematical description of the ordering of the manner in which these oranges have been stacked. This is very analogous to what happens, or to a crystal in materials. How do we describe a crystalline system? The lattice is not enough. For instance, with the oranges, if we want to recreate a tray of oranges, the lattice points are not enough. The lattice points are simply a theoretical construct. We have to repeat something at each lattice point. If we place an orange at each lattice point, in the case of our previous example, we would then recreate the tray of oranges. Similarly, we must place something at each lattice point of the lattice that is being used to describe a crystal to generate the crystal structure. What is repeated at each lattice point is called a basis or a motif. In this diagram, we see how a regular array of fishes can be generated from the lattice shown. As shown below, it doesn't really matter if the fish, when they're placed, are displaced at some fixed displacement relative to the lattice points. If we place one fish at a fixed displacement from the lattice point, we will regenerate the same array of fishes, or generate an array of fishes that have the same arrangement. So a crystal structure is composed of a lattice, which is a set of points, and then a basis or a motif, something we repeat at each lattice point. How do we describe lattice points? We use a unit cell, and a unit cell is a three-dimensional shape that when repeated will generate the crystal. The unit cell is chosen to reflect the geometry and symmetry of the shape. There are many choices of unit shell, but the convention is to choose shapes that reflect the symmetry of the arrangement, and often the corners of the unit cell coincide with the locations of the centers of the atoms in the crystal. Let's have a look at an example of a unit cell. Shown here in A is the unit cell for the face-centered cubic structure. Imagine you had a large number of these, and you started with one, and you put another one directly next to it, like so. We can start to see how we can start to generate a crystal structure if we keep adding blocks in a regular manner. The locations of the atoms within the FCC crystal are shown with these smaller circles in diagram B. And in C, some indication is given of the resulting crystal structure that would arise from repeating the unit cell shown. Unit cells can be primitive or non-primitive. Let's have a look at this regular array of points. The unit cell shown by the parallelogram is the smallest possible, is a unit cell with the smallest possible area. If we made tiles that shape, we could recreate the original array of points. The parallelogram would be a primitive unit cell. However, it would be more conventional to describe the array of points using the rectangle with dots, or a quarter dot at each corner and a full dot at the center. The rectangle is an example of a non-primitive unit cell. The non-primitive unit cell reflects the symmetry of the array in a lot clearer and comprehensible manner. Once we have chosen a unit cell, we must establish the parameters of that cell. And there are 6 possible parameters. The sides, A, B, and C, and the angles between the sides, alpha, beta, and gamma. For instance, the angle between sides C and B can easily is denoted by alpha, because we see that in the ABC sequence, if we look at B and C, A is missing, and so alpha will be the angle between those sides. Similarly, if we have sides A and B, we see that C is missing, and the angle between those two sides will be gamma. And by the same argument, between C and A, the angle between those two is called beta. So this is shown for a general unit cell. However, consider a cubic unit cell, where all the angles are 90 degrees and all the sides are of the same length. In such case, only one parameter is required to describe the size of the unit cell. Through mathematics, it has been shown that there are only 14 types of lattice. These are called the Bravais lattice types. Here they are arranged according to categories. In the top row, we have the cubic lattice types. In the cubic lattice types, all the sides are equal. We see the primitive simple cubic structure denoted by the letter P, and then we have the body-centered cubic denoted by the letter I, and the face-centered cubic structure, which is the example we looked at earlier, is denoted by the letter F. In the tetragonal lattice, we notice that A and B can be of A and B are the same length, but C is of a different length. But the angles are all 0. In an orthorhombic crystal structure, A, B and C are all different, but the angles are all the same and equal to right angles. In the hexagonal unit cell, A is equal to B, but C is different from A and B, and the angles are fixed in a hexagonal cell. In this way, we can count the number of parameters we need to describe these unit cells. For a cubic unit cell, there is only one parameter. For a tetragonal, we need to describe 2, because A and B are equal, but C is not equal to A and B. In an orthorhombic crystal structure, there are 3 parameters. In a hexagonal, there are 2. In a monoclinic, A is not equal to B, which is not equal to C, but the angles are fixed, so there are 3 parameters that need to be known. In the triclinic, A and B and C are all different and the angles are different. So here we see the 14 Bravais lattices arranged into 7 crystal classes. In the next video, we will look at important types of these Bravais lattice types in detail.